Somewhere right now, probably within a few hundred miles of where you are lying, there is a building with no windows. It has concrete walls, a perimeter fence, and security cameras on every corner. There is no sign out front telling you what happens inside. If you drove past it, you might think it was a warehouse, or maybe some kind of utility station. But inside that building, behind layers of locked doors and climate-controlled corridors, thousands of computers are running. They are running right now, at this moment, while you listen to this. They have been running all day. They were running yesterday, and last week, and last month. Some of them have been running, without interruption, for years. Those computers are holding your photographs. They are holding your emails, your documents, your messages, the videos you have watched, the searches you have typed, the files you forgot you saved. They are keeping the apps on your phone working, the websites you visit responsive, the services you rely on available. When someone says your data is in the cloud, this is what they mean. Not a floating ethereal place above the sky. A building, a physical building with a physical address, drawing electricity from the same power grid that lights your house. Tonight we are going to walk through that building and all the systems that make it work. We are going to look at the actual infrastructure behind the word everyone uses but almost nobody sees. We will start with the concrete and the steel, the power lines and the cooling towers. We will move through the layers of software that turn thousands of individual machines into something that behaves like one enormous flexible computer. We will trace how your data gets replicated across buildings that are miles apart, how the network routes your requests through fiber that crosses ocean floors, and how the engineers who run all of this handle the inevitable moment when something breaks. Because something always breaks, and the way these systems fail is as interesting as the way they work. There is no rush. The buildings are not going anywhere. They have been quietly humming underneath everything you do online for years, and they will keep humming after you fall asleep tonight. Let's start with what a data center actually looks like when you walk inside. The first thing you would notice is the sound. Data centers are loud. Thousands of fans are spinning inside thousands of servers, pulling air across circuit boards to carry heat away from processors. On top of that, large industrial cooling units are running constantly, circulating chilled water or cold air through the building to keep the temperature in a narrow range. The combined noise is a deep, steady roar that you feel in your chest as much as you hear in your ears. People who work in these facilities wear hearing protection on the floor. The servers themselves are mounted in tall metal frames called racks. A standard rack is about 6 feet tall, roughly 2 feet wide, and 3 feet deep. Each rack holds dozens of individual servers stacked vertically, each one a flat metal box about 1.5 inches thick. The front of each server has a row of small lights that blink constantly, indicating activity. Network cables and power cables run from the back of each server, bundled together and routed through trays that run along the ceiling or under a raised floor. In a large data center, there can be tens of thousands of these servers arranged in row after row of racks, and the rows stretch the length of a building that might be 200,000 square feet or more. The raised floor is a feature of many older data centers, though newer designs sometimes use overhead cooling instead. In a raised floor design, the actual floor of the building sits about 2 feet below the surface you walk on. The space underneath is a plenum, a pressurized chamber where cold air is pushed by large air handling units. Perforated tiles in the floor allow that cold air to rise into the server aisles, where it flows through the equipment, absorbs heat, and rises to the ceiling. The warm air is then captured and returned to the cooling units, where it is chilled again and recirculated. This creates a continuous loop of cold air flowing up from the floor, through the servers, and back to the cooling systems. Modern data centers often use a design called hot aisle and cold aisle containment. The racks are arranged so that the fronts of the servers, where the cold air enters, all face the same direction in alternating rows. One aisle between 2 rows of racks is the cold aisle, where chilled air is delivered. The next aisle over is the hot aisle, where the exhaust air exits the back of the servers. Physical barriers, plastic curtains or solid panels Seal off either the hot aisle or the cold aisle to prevent the two air streams from mixing. This simple arrangement makes a measurable difference in cooling efficiency, because mixing hot and cold air wastes energy. You end up cooling air that is already cool, or sending warm air back through equipment that needs to stay cold. The cooling itself is one of the largest costs of running a data center, and it is one of the areas where the industry has changed the most over the past 2 decades. Early data centers used conventional air conditioning, essentially the same technology that cools an office building, just scaled up enormously. That works, but it is expensive and energy intensive. A data center that draws 30 megawatts of computing power might need another 10 or 15 megawatts just for cooling, meaning a significant fraction of the total electricity bill goes to moving heat rather than processing data. The ratio between the total energy a data center uses and the energy that actually goes to the computing equipment is called the power usage effectiveness, or PUE. A PUE of 2 means that for every watt of computing power, you are using an additional watt for cooling, lighting, and other overhead. A PUE of 1.2 means that only 20% of the energy goes to non-computing overhead. The industry average has been declining for years. In the early 2000s, a PUE of 2 or higher was common. Today, the most efficient hyperscale data centers report PUE values around 1.1, which means they have reduced overhead energy to about 10% of the total. They achieve this through a combination of techniques. Free cooling, which uses outside air when the temperature permits, is common in cooler climates. A data center in Oregon or Ireland can open its intake vents for most of the year and let the naturally cool outside air flow through the building, using mechanical cooling only during the warmest months. Evaporative cooling, which passes air over water to lower the temperature, works well in dry climates like the American Southwest. Google has experimented extensively with higher operating temperatures, running servers at temperatures that would have been considered dangerously warm a decade ago, because modern server components can tolerate it, and higher operating temperatures reduce the cooling load significantly. Some of the most advanced facilities use liquid cooling, where coolant flows directly over the processors through sealed channels on the circuit board, removing heat far more efficiently than air ever could. Air is a relatively poor conductor of heat compared to liquid, and at the power densities of modern processors, especially the specialized chips used for artificial intelligence workloads, air cooling is approaching its physical limits. Liquid cooling can handle the thermal loads that air cannot, and it does so with less energy, because the coolant absorbs heat more readily and can be pumped with less power than the equivalent volume of air. A few facilities have been built in naturally cold locations, like northern Scandinavia, Iceland, or even underwater. Microsoft ran a project called Project Natick that placed a sealed data center module on the seafloor off the coast of Scotland, using the cold ocean water for cooling and the constant temperature of the deep water to maintain stable thermal conditions. The experiment ran for 2 years and found that the sealed underwater environment actually reduced the failure rate of the servers compared to identical servers in a conventional data center on land, partly because the sealed chamber eliminated the dust, humidity, and temperature fluctuations that contribute to hardware degradation. The project was exploratory, but it demonstrated that the physical form of a data center is more flexible than most people assume. The cold climate facilities in Scandinavia and Iceland have an additional advantage beyond free cooling. They draw on abundant renewable energy from hydroelectric and geothermal sources, which keeps their carbon footprint low. The combination of natural cooling and clean energy makes these locations attractive for companies trying to reduce the environmental impact of their data center operations. But most of the world's data center capacity is not in Scandinavia. It is in places like Northern Virginia, which hosts the densest concentration of data centers on the planet, and where the electricity comes primarily from the regional grid, which includes a mix of natural gas, nuclear, and renewable sources. Now let's look at the power supply itself, because this is where the scale of data centers becomes genuinely hard to grasp. A single large hyperscale data center can draw 20 to 50 megawatts of electrical power continuously. To put that in perspective, a typical American household uses about 1.2 kilowatts on average. So a single data center drawing 30 megawatts is consuming roughly the same amount of electricity as 25,000 homes. And that is one building. The large cloud providers operate dozens of these facilities in a single metropolitan area and hundreds worldwide. Globally, data centers consumed somewhere between 240 and 340 terawatt-hours of electricity in 2022, according to the International Energy Agency. That is between 1 and 1.3% of all the electricity generated on the planet. For context, that is roughly equivalent to the total electricity consumption of a country the size of the United Kingdom. And the demand is growing. It is growing because of the expansion of cloud computing, because of artificial intelligence workloads that require enormous processing power, and because of the steady migration of more and more of daily life onto networked services. The power has to be reliable. A data center that loses power loses everything it was doing at the moment the electricity stopped. Servers crash, connections drop, data in transit is lost. Active computations are interrupted and must be restarted. For the services running on those servers, an unplanned power loss is not a minor inconvenience. It is a potential disaster. So data centers invest heavily in making sure the power never goes out, even when the external grid fails. The first line of defense is redundant power feeds. A well-designed data center connects to the utility grid through two or more independent power paths, often from different substations or different transmission lines. If one feed fails, the other continues to supply power without interruption. Some facilities even draw from two entirely separate utility companies, so that a problem at one provider does not affect the other feed. The switchgear that manages these feeds can transfer the load from one feed to another in milliseconds, fast enough that the servers never see the switch. Behind the utility feeds sit uninterruptible power supplies, commonly called UPS systems. These are large banks of batteries, or in some cases flywheel systems, that sit between the incoming power and the servers. Under normal conditions, the power flows through the UPS without the batteries doing anything. The batteries are being maintained at full charge, quietly waiting. But the moment the incoming power drops or fluctuates even slightly, the UPS instantly switches to battery power, maintaining a perfectly stable electrical supply to the servers. The transition happens in milliseconds, fast enough that the servers never notice the grid went away. The batteries are not meant to run the data center for hours. They are meant to bridge the gap, typically 10 to 15 minutes, until the backup generators come online. In some designs, the UPS uses flywheels instead of batteries. A flywheel is a heavy spinning disc that stores energy as rotational momentum. When the power goes out, the flywheel's momentum drives a generator that produces electricity. Flywheels can respond even faster than batteries, delivering full power within fractions of a second, and they do not degrade with charge cycles the way batteries do. The backup generators are diesel engines, or sometimes natural gas turbines, housed in a separate building or in hardened enclosures outside the data center. When the power goes out, an automated system starts the generators. They reach full power within seconds to a few minutes, depending on the design, and begin supplying electricity to the facility. A large data center might have a dozen or more generators, each one the size of a shipping container, collectively capable of powering the entire facility for as long as the fuel lasts. The fuel tanks hold enough diesel for hours or even days of operation, and contracts with fuel suppliers guarantee resupply within a defined time frame if the outage extends longer. This layered approach, redundant utility feeds, UPS batteries or flywheels for the immediate gap, diesel generators for extended outages, is the standard architecture for keeping a data center running through a grid failure. The layers overlap deliberately. The UPS covers the time the generators need to start. The generators cover any length of outage the utility might have, and the redundant feeds mean that many outages never require the UPS or generators at all, because the second feed picks up the load before the batteries are needed. But the power system does not end at the building's electrical panel. Inside the data center, the power is distributed through a hierarchy of switchgear, transformers, and distribution panels that route electricity to individual rows and individual racks. At each level of the hierarchy, there are redundant paths. A server rack might receive power from two separate distribution panels, each one fed by a different power chain all the way back to the utility. And each server inside the rack might have two power supplies connected to those two panels independently. If one power supply fails, or one distribution panel fails, or one entire power chain fails, the server keeps running on the other. This redundancy extends all the way from the utility feed to the individual circuit board inside a single machine. The industry describes these levels of redundancy using a classification system developed by the Uptime Institute. The tiers range from 1 through 4. A Tier 1 facility has a single path for power and cooling and no redundancy. It can be taken offline for maintenance, and an unplanned failure takes the computing equipment down. A Tier 2 facility adds redundant components, like a backup generator, but still has a single distribution path. A Tier 3 facility has multiple distribution paths, but only one is active at a time. It can be maintained without taking the computing equipment offline, because the second path carries the load during maintenance. A Tier 4 facility has multiple independent, simultaneously active paths. Any single failure, and in some cases any two simultaneous failures, can be absorbed without affecting the computing equipment. Most of the large cloud providers' data centers are built to Tier 3 or Tier 4 standards, though the providers often design to their own internal specifications that may exceed the formal tier definitions. Amazon, Google, and Microsoft each publish detailed information about their data center designs, and the level of engineering that goes into the physical infrastructure is remarkable. Every component, from the utility feed to the server power supply, has been analyzed for its failure modes and backed by at least one layer of redundancy. And yet, with all of this engineering, outages still happen. Before we get to why, we need to understand what all this hardware actually does when it is running, because the physical building is only the beginning. The real complexity lives in the software layers that sit on top of the hardware and turn thousands of individual machines into the thing people call the cloud. Let's step back for a moment and think about what the word cloud actually means in practical terms, because the word itself is almost perfectly misleading. It suggests something airy and intangible, something that floats above the physical world. The reality is the opposite. The cloud is one of the most physical, most material things in modern technology. It is steel, copper, silicon, and fiber-optic glass, consuming electricity, generating heat, and occupying real estate. When you store a photograph on your phone and it appears in your account on a different device, the photograph was sent from your phone over the network to a server in one of these data centers, stored on a disk in that server, and then retrieved by the other device when it asked for it. That much is straightforward. A server received data, stored it, and served it again later. Servers have been doing that since the 1990s. What makes cloud computing different from traditional server hosting is a set of ideas about how the servers are organized, how the work is divided, and how the resources are shared. The National Institute of Standards and Technology, which is a branch of the United States Department of Commerce, published a formal definition that captures the essential characteristics. 5 things distinguish cloud computing from older models of running servers. First, on-demand self-service. You can provision computing resources, a server, a database, a block of storage, without needing to talk to a human being at the data center. You log into a web console, select a few options, and the resources appear. Seconds later, you have a machine running that did not exist a minute ago. Second, broad network access. The resources are available over the network and can be reached from any standard device. A laptop, a phone, a tablet, a workstation on the other side of the world. You do not need to be in the same building or on the same local network as the server. Third, resource pooling. The provider's computing resources are pooled and shared among many customers using a model called multi-tenancy. Your workload might be running on the same physical machine as someone else's workload, separated by software boundaries, but sharing the same hardware underneath. The customer generally does not know or control which specific physical machine their workload runs on. The provider manages the allocation, and the customer sees an abstraction. Fourth, rapid elasticity. Resources can be scaled up or down quickly, often automatically, to match demand. A website that normally handles a few thousand visitors per hour can automatically add more computing capacity when 1 million visitors arrive at once, and release that capacity when the traffic subsides. From the customer's perspective, the available resources appear to be infinite, even though underneath they are drawn from a finite pool of physical hardware. Fifth, measured service. Resource usage is monitored, measured, and reported, and the customer pays only for what they use. Like a utility, you are billed for consumption, not for reservation. If your server runs for 3 hours, you pay for 3 hours. If it sits idle, many configurations charge you nothing. These 5 characteristics together describe something fundamentally different from renting a dedicated server in a data center, which is what businesses did before cloud computing became widespread. In the older model, you rented a specific physical machine, or you bought your own machine and placed it in a data center, paying for power, cooling, and a network connection. That machine was yours. Nobody else used it. If you needed more capacity, you ordered another machine and waited days or weeks for it to arrive, be installed, and be configured. If demand dropped, you were still paying for the machine, whether it was busy or idle. Cloud computing replaced that model with something far more flexible, and the key technology that made it possible is virtualization. Virtualization is the idea of taking a single physical computer and dividing it into multiple virtual computers, each one behaving as if it were a complete, independent machine with its own operating system, its own memory, its own processors, and its own storage. The software that manages this division is called a hypervisor. It sits between the physical hardware and the virtual machines, allocating real resources, processor time, memory, disk space, network bandwidth, among the virtual machines running on top of it. From inside a virtual machine, the experience is indistinguishable from using a real physical computer. The operating system sees what appears to be a normal set of hardware. Applications run without knowing or needing to know that they are sharing a physical machine with other virtual machines. The isolation between virtual machines is maintained by the hypervisor, which ensures that one virtual machine cannot access the memory, storage, or network traffic of another. This technology was not invented for cloud computing. Virtualization has its roots in mainframe computing in the 1960s, when IBM developed systems that could run multiple operating systems simultaneously on a single large computer. The concept was called time sharing, and it allowed multiple users to share the expensive mainframe hardware without interfering with each other's work. Each user saw what appeared to be their own private machine, even though they were all using the same physical computer. The idea migrated to commodity server hardware in the late 1990s and early 2000s, driven by a company called VMware. VMware's ESX hypervisor, released in 2001, made it practical to run multiple virtual machines on standard x86 servers, the same kind of servers you could buy from Dell or HP. This was a significant shift because it meant that the benefits of virtualization, efficient hardware utilization, easy provisioning, isolation between workloads, were available on the inexpensive hardware that most companies were already using, not just on specialized mainframes. Later, the open-source KVM hypervisor, which was built into the Linux kernel starting in 2007, made virtualization even more accessible. KVM turned any Linux server into a hypervisor without requiring additional software licenses, and it became the foundation for many cloud computing platforms. The cloud providers took virtualization further than anyone had done before. Amazon Web Services, which launched its Elastic Compute Cloud service in 2006, was among the first to offer virtualized servers to the public on a pay-per-hour basis. A developer who needed a server for a project could provision one in minutes, use it for as long as needed, and shut it down when the work was done. No hardware to buy, no data center to visit, no contract to negotiate. The server existed for as long as the customer needed it and vanished afterward. The launch of Amazon's cloud computing services was not originally planned as a separate business. It grew out of Amazon's own internal need to provide reliable infrastructure for its rapidly growing retail operation. The company had built the internal tools to provision and manage servers quickly and efficiently for its own engineering teams, and it realized that the same tools could be offered to outside customers. What started as an internal infrastructure project became one of the most consequential products in the history of the technology industry. Google and Microsoft followed with their own cloud platforms, Google Cloud Platform and Microsoft Azure, and over the following decade, the cloud computing industry grew into a market worth hundreds of billions of dollars per year. Today, Amazon Web Services, Microsoft Azure, and Google Cloud are the three largest providers, but there are many others, including IBM, Oracle, Alibaba, and a range of smaller regional and specialized providers. The hypervisor is only the first layer of abstraction. On top of it sit layers of software that manage the fleet of virtual machines across thousands of physical servers. These systems, sometimes called orchestration layers or control planes, handle the decisions about which physical server should host which virtual machine, how to balance the load across machines, how to move a virtual machine from one physical server to another if maintenance is needed, and how to restart a virtual machine on a different server if its original host fails. The control plane is the brain of the cloud. It receives requests from customers, allocates resources, monitors the health of every machine, and responds to failures. When you ask a cloud provider for a new virtual machine, the control plane selects a physical server with enough available capacity, instructs the hypervisor on that server to create the virtual machine, assigns it network addresses, connects it to the requested storage, and reports back that the machine is ready. All of this happens in seconds, with no human intervention. The control plane also handles something called live migration, which is one of the more remarkable capabilities of modern cloud infrastructure. A running virtual machine, with its operating system active and its applications processing requests, can be moved from one physical server to another while it continues to run. The hypervisor on the source machine copies the virtual machine's memory to the destination machine in the background, page by page, while the virtual machine keeps working. Each page of memory is copied, and if a page is modified after it was copied, it is marked for recopying. This iterative process continues until only a small number of rapidly changing pages remain. At that point, the virtual machine is briefly paused, the final changes are transferred, and the virtual machine resumes on the new host. The entire process can take just a few hundred milliseconds of pause time, short enough that most applications never notice the interruption. This capability allows the cloud provider to perform hardware maintenance, replace failing components, or rebalance workloads across the data center without disrupting the customer's service. A server that needs a firmware update or a memory module replacement can have all its virtual machines migrated to other servers, the maintenance performed, and the virtual machines migrated back, all without the customers knowing anything happened. Beyond virtual machines, the cloud providers offer a much broader set of building blocks that customers can assemble into applications. Storage services hold data reliably and make it available from anywhere. Database services manage structured data and handle the complexity of queries, indexing, transactions, and backups. Messaging services let different parts of an application communicate asynchronously without being directly connected. Content delivery services cache copies of data at locations around the world so that users in different cities and different countries all get fast responses. Machine learning services provide access to specialized processors designed for training and running artificial intelligence models, and there are dozens more, each one abstracting away a piece of infrastructure that a company would otherwise have to build and maintain on its own. All of these services run on the same physical hardware, in the same data centers, managed by the same control plane software. The cloud is not a single technology. It is a stack of technologies, each layer building on the one below, turning physical machines in physical buildings into a flexible, programmable infrastructure that anyone with a credit card and an internet connection can use. Now let's look at how that infrastructure is organized geographically, because the physical location of your data matters more than you might expect. The large cloud providers divide the world into regions. A region is a geographic area, usually a metropolitan area or a section of a country, where the provider operates a cluster of data centers. Amazon Web Services, as of this recording, operates 33 regions worldwide, spanning North America, South America, Europe, Asia, Australia, Africa, and the Middle East. Google Cloud and Microsoft Azure have similar footprints, each with their own set of regions distributed across the globe. The number of regions continues to grow as the providers expand into new markets and as regulatory requirements in different countries demand local data storage. Within each region, the provider operates multiple availability zones. An availability zone is one or more data center buildings that are physically separate from the other zones in that region. Separate buildings, separate power feeds from separate utility substations, separate cooling systems, and separate network connections. The zones within a region are close enough to each other, typically within 100 kilometers, that data can travel between them with very low latency, just a few milliseconds. But they are far enough apart that a localized event, a power grid failure, a natural disaster, a fire, a flood, is unlikely to affect more than one zone at a time. The purpose of availability zones is fault isolation. If a customer's application runs in only one availability zone, and that zone experiences a failure, the application goes down. But if the customer designs their application to run simultaneously in 2 or 3 availability zones within the same region, the application can survive the loss of any single zone. When one zone goes dark, a load balancer automatically redirects traffic to the surviving zones, and the application keeps running. The users might experience a brief increase in latency as the traffic is rerouted, but they do not experience a complete outage. This design principle, running in multiple independent zones, is one of the most important ideas in cloud architecture. The cloud providers encourage it in their documentation, their training materials, and their pricing models, but it requires the customer to design their application specifically for this kind of resilience. The cloud does not automatically make your application fault-tolerant. It gives you the building blocks for fault tolerance, the independent zones, the load balancing, the data replication, and then it is up to you to assemble them correctly. An application that was designed to run on a single server and was simply moved into the cloud without modification does not gain any of these benefits. It sits in a single availability zone, on a single virtual machine, and if that zone fails, the application fails with it. The same principle extends to the regional level. If a customer needs to survive the loss of an entire region, perhaps because of a large-scale natural disaster or a widespread infrastructure failure, they can deploy their application across multiple regions on different continents. This is more complex and more expensive because data has to be replicated across much greater distances, the latency between regions is higher, and the engineering required to keep data consistent across regions that may be thousands of miles apart is substantially more difficult. But for services that truly cannot tolerate any downtime, multi-region deployment is the standard approach. And here is where the architecture of the cloud starts to reveal something important about how it is designed. The cloud is not built to prevent failures. It is built to survive them. The distinction matters more than it might seem at first. A system designed to prevent failures tries to make every component perfectly reliable. Every server always works. Every network link never drops. Every power supply never fails. That approach is impossible at scale. When you operate hundreds of thousands of servers across dozens of data centers, hardware failures are not exceptional events. They are statistical certainties. Hard drives fail, memory chips develop errors, network cards stop responding, power supplies burn out, fans seize. Circuit boards develop intermittent faults. At the scale of a large cloud provider, these things happen every minute of every day. If you have 100,000 hard drives, and each one has a mean time between failure of 5 years, you can expect roughly 50 drives to fail every single day. So instead of trying to prevent individual failures, the cloud is designed to expect them and route around them. The software layers we talked about, the control plane, the hypervisors, the orchestration systems, are constantly monitoring every piece of hardware and reacting when something breaks. A server stops responding, and the control plane automatically restarts its virtual machines on other servers. A hard drive shows signs of impending failure, reporting increasing error rates in its internal diagnostics, and the storage system copies the data to a healthy drive before the old one dies. A network link goes dark, and traffic reroutes through alternative paths. All of this happens automatically, without any human intervention, thousands of times per day. This design philosophy has a name in the industry. It is called designing for failure, and it fundamentally changes how engineers think about reliability. Instead of asking, how do we make sure this component never fails, they ask what happens when this component fails, and is the system's response acceptable? The answer to the second question drives the architecture. Every component has a failure mode, and every failure mode has a planned response. Let's look at how this applies to something critically important, the storage of your data. When you upload a file to a cloud storage service, something like Amazon's Simple Storage Service, commonly called S3, or Google Cloud Storage, that file does not simply sit on a single hard drive in a single server. If it did, and that hard drive failed, your file would be gone. Instead, the storage service creates multiple copies of the file and distributes them across different physical locations. The exact approach varies by provider and by storage class, but a common design uses a technique called erasure coding, which is more sophisticated than simply making 3 copies of the file. Erasure coding breaks the file into fragments and creates additional parity fragments so that the original data can be reconstructed from any sufficiently large subset of the total fragments. For example, a file might be broken into 6 data fragments and 4 parity fragments, stored across 10 different servers or storage devices. Any 6 of the 10 fragments are enough to reconstruct the complete original file. This means that up to 4 of the 10 devices can fail simultaneously, and the data is still fully recoverable. Erasure coding is more storage efficient than simple replication. Making 3 complete copies of a file triples your storage costs. Erasure coding is more storage efficient than simple replication. Erasure coding is more storage efficient than simple replication, while using only about 67% more storage than the original file, rather than 300% more. The trade-off is computational complexity. Encoding and decoding the fragments requires processing power that simple copying does not. But at the scale of a cloud storage service handling billions of objects, the storage savings more than justify the computational cost. The fragments are distributed across multiple availability zones within a region, so that the failure of any single zone, and even the simultaneous failure of multiple storage devices across zones, cannot result in data loss. The storage service runs continuous background processes that check the integrity of every stored fragment, detect corruption, and create new fragments to replace any that are lost or damaged. This process runs constantly, around the clock, verifying and repairing the stored data. Amazon Web Services publishes a durability figure for its standard storage class of 11 nines. Written out, that is 99.999999999%. What that number means in practical terms is that if you stored 10 million objects, you could statistically expect to lose one of them once every 10,000 years. That level of durability is achieved not through any magical hardware, but through the relentless application of redundancy, distribution, and continuous verification. But durability and availability are not the same thing, and this is a distinction worth understanding clearly. Durability means your data still exists. It is safely stored somewhere, intact and recoverable. Availability means you can reach it right now. A storage service can be perfectly durable, with every bit of your data safely stored across multiple zones, and still be unavailable if the network path between you and the service is broken, or if the service's control plane is down, or if the API that manages access to the data is experiencing a failure. These are different kinds of failures, and they require different kinds of engineering to prevent. Durability is about making sure the bits survive on physical storage devices. Availability is about making sure the systems that serve those bits to you are running. You can have high durability and low availability, meaning your data is safe, but you cannot access it. Or you can have high availability and lower durability, meaning you can always access your data, but there is a higher risk that some of it might be lost. The cloud storage services aim for both, but the engineering challenges are different for each. And this is a good moment to look at what sits between you and the data center, because the network is its own vast piece of infrastructure, and it has its own failure modes that are quite different from the failures that occur inside the building. When you access a cloud service, your request travels from your device through your local network to your internet service provider, across the internet's backbone infrastructure, and into the cloud provider's network. The cloud providers operate their own private backbone networks, vast fiber-optic networks that connect their data centers to each other and to the internet exchange points where they exchange traffic with other networks. These backbone networks are separate from the public internet. They are private highways that the providers built and maintain specifically for carrying their customers' traffic with controlled quality and predictable performance. Google, for example, has built one of the largest private networks in the world, connecting its data centers across continents through dedicated fiber. The company has invested in its own submarine cables, owning or co-owning cables that cross the Atlantic and the Pacific. When a user in London searches for something on Google, the query travels from the user's internet provider to a Google point of presence, enters Google's private network, travels across that private network to whatever data center can best serve the query, and the answer comes back the same way. The data spends as little time as possible on the public internet and as much time as possible on Google's own infrastructure, where the company controls the routing, the capacity, and the quality. The backbone networks are built for redundancy. Every major route has at least 2 independent fiber paths, and usually more. If a cable is cut, whether by a construction crew with a backhoe or a fishing trawler dragging its gear across the ocean floor, the traffic automatically reroutes to the surviving paths. The rerouting happens at the network layer, using protocols that detect the failure and recalculate paths within seconds. The engineers design the capacity of each path, assuming that any other single path might fail, so the surviving paths have enough bandwidth to absorb the redirected traffic without becoming congested. But the fiber itself is a physical thing, and physical things can be damaged in ways that are difficult to anticipate. The submarine cables that carry traffic between continents are particularly interesting, both for what they are and for how vulnerable they can be. These cables lie on the ocean floor, sometimes at depths of several kilometers, stretching thousands of kilometers between landing stations on different continents. Over 95% of intercontinental internet traffic travels through these cables. There are roughly 530 active or planned submarine cables worldwide as of 2024, and they carry the vast majority of the data that flows between countries separated by ocean. Satellites carry a tiny fraction of this traffic. The internet is not in the air, it is under the water. A submarine cable is about the diameter of a garden hose in its deep water sections, though it varies in shallow water, where it needs armor plating against anchors and fishing equipment. At its core are optical fibers, typically multiple pairs of fibers, each pair carrying data using pulses of laser light. The fibers are surrounded by layers of insulation, waterproofing, and strength members that protect against the pressure and the corrosive effects of seawater. In shallow water sections, an outer layer of steel armor wire adds protection against physical damage. Along the length of the cable, at intervals of roughly 60 to 100 kilometers, are repeaters. These are small sealed devices, powered by electricity carried through the cable itself as a direct current flowing through a copper conductor alongside the fibers that amplify the optical signals to keep them strong over the enormous distances involved. Without repeaters, the light pulses would weaken and distort until they became unreadable after a few hundred kilometers. The repeaters regenerate the signal, allowing it to travel thousands of kilometers without degradation. Laying a new transoceanic cable is a multi-year project that costs hundreds of millions of dollars. The route is carefully surveyed to avoid underwater mountains, volcanic vents, areas of heavy fishing activity, and zones where earthquakes are frequent. Specialized cable-laying ships carry the cable on enormous drums and lower it to the ocean floor as the ship moves along the planned route. The process can take months for a long route, and the ship must maintain a precise course to place the cable along the surveyed path. When a cable breaks, the consequences depend on how many other cables serve the same route. Between North America and Europe, there are dozens of submarine cables, and losing one has relatively little noticeable impact because traffic shifts to the others. The redundancy is substantial, and the network was designed to tolerate multiple simultaneous cable failures on these heavily trafficked routes. But between some regions, there are only one or two cables, and losing the only cable to a remote area can be severe. In January of 2022, the eruption of the Hunga Tonga volcano in the South Pacific severed the single submarine cable connecting the island nation of Tonga to the global internet. The eruption was one of the most powerful volcanic events in decades, sending a shockwave that circled the planet multiple times and generating tsunami waves across the Pacific. The cable, which connected Tonga to Fiji and from there to the rest of the world, was severed by the eruption's underwater effects, likely a combination of the volcanic debris flow and the seismic activity. Tonga was left almost entirely without internet connectivity for over 4 weeks, until a specialized cable repair ship could reach the area and splice the damaged sections. The ship had to locate the breakpoints, recover the cable from the ocean floor, splice in new sections of fiber, and lower the repaired cable back to the seabed. The repair operation is itself an impressive piece of engineering, performed from a moving ship in open ocean, handling delicate optical fibers and powered repeaters that must function reliably for decades on the seafloor. 4 weeks without internet in 2022 for an entire country. Banking, communications, government services, education, all affected. That is what happens when a connection has no redundancy, when there is only one physical path, and that path is destroyed. The story of Tonga illustrates something that the cloud, for all its layers of software abstraction, cannot escape. The cloud runs on physical infrastructure, and physical infrastructure exists in the physical world. It can be shaken by earthquakes, flooded by storms, severed by volcanoes, or cut by a ship's anchor. The abstraction layers, the virtualization, the orchestration, the automatic failover, all of it depends ultimately on buildings that need electricity, cables that need to stay intact, and machines that need to keep running. The cloud is not immune to geography, it is embedded in it. Now let's talk about what happens inside the data center's network, because the internal networking of a cloud data center is its own complex system with its own interesting design choices and failure modes. Inside a large data center, the servers are connected to each other and to the outside world through a hierarchy of network switches. At the lowest level are the individual servers, each one connected by a cable to a switch at the top of its rack, called a top-of-rack switch. That switch aggregates the traffic from all the servers in that rack, typically 20 to 40 servers, and connects upward to the next level of the network. In older data center designs, the top-of-rack switches connected to aggregation switches, which served multiple racks, and the aggregation switches connected to core switches at the center of the network. This hierarchical, tree-shaped design is simple and well understood, but it creates potential bottlenecks. Two servers in the same rack can communicate at the full speed of their local connections, but two servers on opposite sides of the data center have to send their traffic all the way up the tree to the core and back down, sharing bandwidth with every other cross-rack communication along the way. The bandwidth available between distant servers can be significantly less than the bandwidth between nearby servers. Modern data center networks have moved toward a design called a closed network, named after the telephone switching researcher Charles Close, or sometimes called a leaf spine architecture. In this design, every leaf switch, which replaces the top of rack switch, connects to every spine switch in the layer above. There is no aggregation layer in between. This means that any two servers can communicate through at most two hops, one up to a spine switch and one back down to the destination leaf switch. Because every leaf connects to every spine, there are many parallel paths between any two servers, and the bandwidth between any two servers is roughly equal regardless of their physical location in the data center. This design requires more switches and more cables than the traditional tree, but it eliminates the bottleneck problem and provides much more uniform, predictable network performance. For cloud workloads, where thousands of servers need to communicate with each other continuously, exchanging data between components of distributed applications, predictable network performance is worth the additional cost. On top of the physical network hardware sits another layer of abstraction, the software-defined network. In a traditional network, each switch makes its own forwarding decisions based on routing tables that it builds by exchanging information with neighboring switches. In a software-defined network, a central controller maintains a global view of the network's topology and traffic patterns, and it programs the forwarding rules in each switch according to a centralized policy. This gives the cloud provider much finer control over how traffic flows through the data center, how bandwidth is allocated among customers, how security policies are enforced, and how the network responds to failures and congestion. Software-defined networking is also what allows cloud providers to offer virtual networks to their customers. A customer can create what appears to be a private network with its own address space, its own subnets, its own routing rules, and its own security boundaries, all running on top of the shared physical network. The isolation between customers is enforced in software using encapsulation techniques that wrap each customer's packets in an outer header, identifying which virtual network they belong to. The physical switches route based on the outer header. The destination strips off the outer header and delivers the original packet to the customer's virtual machine. The customer sees a private, isolated network. The physical infrastructure sees labeled packets flowing through a shared fabric. This is another example of the layered abstraction that defines cloud computing. Each layer presents a simplified view of the layer below, hiding the complexity and allowing each level to be designed, managed, and improved independently. Now let's talk about containers, because they represent another important layer in the stack, and they have changed how modern applications are built and run on cloud infrastructure. We talked about virtual machines, where a hypervisor creates the illusion of a complete computer with its own operating system. Containers take a different approach. Instead of simulating an entire computer, a container shares the host operating system's kernel and isolates only the application and its immediate dependencies. Each container has its own view of the file system, its own network interface, its own process space, but all the containers on a server share the same underlying operating system kernel. Because containers do not need to run a full operating system each, they are much lighter than virtual machines. A container might start in less than a second, compared to the tens of seconds or minutes that a virtual machine can take to boot. A container might use only tens of megabytes of memory for its overhead, compared to the hundreds of megabytes or gigabytes that a virtual machine's operating system requires. And a single physical server might host hundreds of containers, compared to the tens of virtual machines that the same server could support. The tool that brought containers to mainstream adoption was Docker, released in 2013. Docker provided a standardized way to package an application, along with all its libraries, configuration files, and dependencies, into a container image. That image could be run on any server with the Docker runtime installed, and it would behave identically regardless of the underlying hardware or operating system version. A developer could build and test an application on their laptop, package it as a Docker container, and deploy it to a server in a data center with confidence that it would work the same way. On top of Docker, an orchestration system called Kubernetes, originally developed inside Google and released as open-source software in 2014, became the standard way to manage containers at scale. Kubernetes automates the deployment, scaling, and operation of containerized applications across a cluster of servers. It decides which server should run which container based on available resources. It restarts containers that crash. It scales the number of container instances up or down based on demand. It handles the network routing that allows containers to discover and communicate with each other. And it performs rolling updates, replacing old versions of a container with new versions gradually, so that the application remains available throughout the deployment process. Google developed Kubernetes based on its internal system called Borg, which the company had used for over a decade to manage its own vast container workloads. By releasing Kubernetes as open-source software, Google effectively set the industry standard for container orchestration, and the system has been adopted by all the major cloud providers and by thousands of companies running their own infrastructure. The combination of containers and Kubernetes has become the dominant way that modern cloud applications are built and operated. It adds another layer of abstraction on top of virtual machines, which sit on top of hypervisors, which sit on top of physical hardware. Each layer hides the complexity of the one below and presents a simpler interface to the one above. And each layer introduces its own potential failure modes. A misconfigured Kubernetes deployment might send all traffic to a single container instance, overwhelming it while others sit idle. A container might crash and be restarted on a different server, losing any data it held in memory that was not persisted to external storage. A resource limit set too low might cause a container to be killed by the orchestration system when it tries to use more memory than its allocated share. The abstractions simplify the normal case, but can make failures harder to diagnose, because the problem might originate in any layer and manifest differently at each level of the stack. Let's take a breath here and appreciate the full picture of what we have built up. We started with a building, concrete walls, no windows, a deep, steady roar from the cooling systems. Inside, thousands of servers in metal racks, cooled by carefully designed airflow systems, powered by redundant electrical feeds backed by batteries and diesel generators. On top of the hardware, hypervisors create virtual machines that share the physical resources. Control planes manage the fleet of virtual machines across the data center. Storage systems split data into fragments and distribute them across availability zones, verifying and repairing continuously. Networks of fiber-optic cable and switches connect everything together, with software-defined layers providing isolation and control. Containers and orchestration systems add yet another level of abstraction for running modern applications. All of it exists to do one thing: to make computing resources available to anyone, anywhere, at any time, as reliably as possible. And most of the time, it works remarkably well. Billions of people use cloud services every day without thinking about any of this, the same way people use electricity without thinking about power plants and transmission lines. But sometimes it breaks, and when it breaks at scale, the effects are sudden, widespread, and strange in ways that reflect the complexity of the systems involved. Because the same interconnection and automation that make the cloud powerful also create pathways for failures to propagate in ways that surprise even the people who built the systems. Let's look at specific examples, because the best way to understand how the cloud fails is to study real failures and trace what actually happened. On October 4, 2021, Facebook disappeared from the internet. not just the social media platform. Everything the company operated: Facebook, Instagram, WhatsApp, Messenger, the Oculus virtual reality platform, and all the internal tools that the company's tens of thousands of employees used for their daily work. All of it went offline, simultaneously, and stayed offline for approximately 6 hours. The cause was a configuration change to the backbone routers that carry traffic between Facebook's data centers. Facebook's network engineering team issued a command that was intended to assess the capacity of the backbone network. The command was supposed to run a diagnostic check, but the command contained an error, and instead of assessing capacity, it withdrew the border gateway protocol route advertisements that told the rest of the internet how to reach Facebook's network. To understand why this matters, you need to know a little about how networks find each other on the internet. The internet is not one network. It is a collection of tens of thousands of separate networks, called autonomous systems, that have agreed to exchange traffic with each other. Each autonomous system uses a protocol called BGP, the Border Gateway Protocol, to announce to its neighbors which internet addresses it can serve. When Facebook's routers announce their BGP routes, they are saying, if you want to reach any of these addresses, send the traffic to us. Every other network on the internet receives these announcements and uses them to build routing tables that tell their own routers where to forward traffic destined for Facebook. When Facebook's routers withdrew those announcements, every other network on the internet lost the information about how to reach Facebook. Within minutes, Facebook's addresses were removed from the routing tables of networks around the world. The servers were still running, the data was still stored, the data centers still had power, but nobody could reach any of it because the internet no longer knew the path. The effects cascaded immediately. WhatsApp, which serves over 2 billion users worldwide, stopped working. Instagram went dark. Companies that used Facebook login as their authentication system, allowing users to sign into their services using their Facebook credentials, found that their own users could not sign in. Advertisers lost access to their campaigns and their analytics. News organizations that relied on Facebook for distributing content lost their audience. And critically, Facebook's own employees lost access to their internal tools. This last point deserves emphasis because it illustrates a dependency that nobody had fully thought through. Facebook's internal communication systems, their corporate messaging platforms, their monitoring dashboards, their incident management tools, their documentation systems, all ran on the same infrastructure that had just gone offline. The engineers who needed to diagnose and fix the problem could not use their normal tools to communicate with each other. They could not pull up the monitoring dashboards that would show them what had happened. They could not access the documentation that described the network configuration. Some reports describe engineers being physically unable to enter data center buildings because the electronic badge access system that controlled the doors depended on the same network that was now down. The building's security system needed to communicate with a server to verify an employee's badge, and that server was unreachable. The physical security system, designed to protect the data center, was preventing the people who needed to fix the problem from reaching the equipment. The fix required engineers to physically travel to data centers, gain manual access to the router consoles, and reverse the configuration change that had caused the withdrawal of the BGP routes. It took approximately 6 hours from the start of the outage to full restoration of services. What makes this outage genuinely instructive is its mechanism. This was not a hardware failure. No server burned out, no cable was cut, no power went out, no earthquake shook the building. The physical infrastructure was running perfectly the entire time. The failure was purely logical, a single configuration command that propagated through the network's own systems and erased Facebook's presence from the global routing infrastructure. The servers were there, the data was safe, nobody could find any of it. This is a pattern that appears again and again in large-scale cloud failures. The hardware works fine. The software, responding to a human command or an automated process, makes a change that has unintended consequences, and those consequences propagate faster than any human can react. The speed of propagation is part of the problem. The same infrastructure that distributes configuration changes across the entire network in seconds, which is normally a feature that ensures consistency, becomes a vulnerability when the change being distributed is wrong. The tool that keeps the system coherent becomes the tool that breaks it everywhere at once. On December 14, 2021, Amazon Web Services experienced an outage in its US East 1 region, the company's largest and oldest region, based in Northern Virginia. The outage lasted approximately 11 hours and affected a wide range of services and the companies that depended on them. The root cause, according to Amazon's detailed post-incident summary, was an automated scaling activity in the internal network that connects AWS services to each other. This internal network is separate from the network that carries customer traffic. It is the backbone that AWS's own services use to communicate, to authenticate requests, to access shared databases, and to coordinate their operations. You could think of it as the nervous system of the cloud, the network that the cloud uses to talk to itself. The automated scaling system was adding capacity to this internal network, which was a routine operation that had been performed many times before without incident. But on this occasion, the scaling activity triggered an unexpectedly large amount of connection activity. The automated system requested more capacity, and in doing so, it generated a surge of network connections that overwhelmed the devices responsible for routing traffic on the internal network. Those devices became congested, their queues filled up, and they began dropping connections and delaying responses. The congestion on the internal network immediately began affecting every AWS service that depended on it. Services that needed to authenticate requests found that the authentication system was slow or unresponsive because the authentication system depended on the congested internal network. Services that depended on those services began failing in turn. Services that depended on those services failed next. The failure cascaded outward through layer after layer of dependencies. Disney Plus went down. Ring doorbells stopped responding to their owners. Roomba vacuums could not connect to their cloud control servers and sat idle on their charging docks. Instacart, the grocery delivery service, could not process orders. Parts of the Associated Press news distribution system were affected. The delivery app for a national restaurant chain stopped working. The connected doorbell of a homeowner could not notify them that a package had been delivered. The outage lasted approximately 11 hours, during which AWS engineers worked to restore the internal network capacity, drain the backlogs, and restart the affected services in a controlled sequence. The recovery itself required careful coordination, because simply bringing all the affected services back online simultaneously would have created another surge that could have overwhelmed the network again. The engineers had to bring services back gradually, monitoring the network load at each step. The December 2021 outage illustrates a concept that is central to understanding how the cloud fails, the concept of a shared dependency. Modern cloud applications are not monolithic programs running on a single machine. They are composed of dozens or hundreds of individual services, each one depending on other services to function. A web application might depend on a database service, an authentication service, a storage service, a caching service, a notification service, and a monitoring service. Each of those services depends on others. The database depends on a storage backend and a networking service. The authentication service depends on a directory service and a key management service. The dependency graph can be enormous and deeply nested. At the bottom of this dependency graph, in any large cloud system, sit the shared infrastructure services that everything else relies on: the internal network, the identity and access management service, the DNS resolution service, the metadata service that tells virtual machines about their own configuration. These foundational services are used by everything, and when one of them fails, the failure propagates upward through the entire dependency tree. The providers work extremely hard to make these foundational services robust. They are typically the most carefully engineered, most heavily monitored, most thoroughly tested services in the entire fleet. But they are still software, running on hardware, maintained by humans, and they can still fail. When they do, the impact is disproportionate, because everything above them in the stack depends on them. This is the problem of cascading failures, and it is one of the most studied problems in distributed systems engineering. The features that make cloud computing powerful, the deep interconnection of services, the automatic scaling, the shared infrastructure, the rich dependency graphs, also create pathways for failures to spread in ways that are difficult to predict and difficult to contain. The cloud providers invest enormous engineering effort in building defenses against cascading failures. They design services to degrade gracefully under stress, returning partial results instead of complete errors, or serving cached data when the live data source is unavailable. They implement circuit breakers, software components that detect when a dependency is failing and temporarily stop calling it, giving it time to recover instead of piling more requests onto an already overwhelmed service. They use bulk heading, dividing a service into independent partitions so that a failure in one partition does not spread to the others. They design their systems to shed load when they become overwhelmed, deliberately rejecting some requests to preserve the ability to serve the rest. Netflix, which runs its streaming service on Amazon Web Services, pioneered the practice of chaos engineering, deliberately injecting failures into production systems to discover how the systems respond and to fix weaknesses before real failures exploit them. Their tool, called Chaos Monkey, randomly terminates virtual machines in the production environment to ensure that the streaming service can tolerate the loss of any individual machine without affecting what viewers see on their screens. They later expanded this to Chaos Gorilla, which simulates the loss of an entire availability zone, and Chaos Kong, which simulates the loss of an entire AWS region. The names are deliberately whimsical, but the practice is serious and methodical. The principle behind it is simple. If you have not tested how your system responds to a failure, you do not know how it will respond. And the worst time to find out is during an actual production incident, when real customers are affected and the pressure to restore service is intense. But even with chaos engineering, circuit breakers, bulk heading, and graceful degradation, large-scale outages continue to happen. They continue because the systems are genuinely complex, and complex systems produce emergent behaviors that testing cannot fully anticipate. A specific sequence of automated actions interacts with a specific state of the network in a way that nobody predicted. A routine maintenance operation triggers a latent bug in software that has been running correctly for months. A cooling system fails, and the thermal management system responds by migrating workloads to another zone, which overloads that zone's capacity. The specific chain of events is different every time, but the underlying dynamic is the same. Multiple components, each working correctly in isolation, interact in a way that produces a system-level failure that none of them could have produced alone. Let's look at another example that illustrates a different type of failure, one that starts with the physical infrastructure rather than the software. In September of 2020, Microsoft Azure experienced a significant outage in its south-central US region, based in Texas. The cause was a cooling failure in one of the data centers. The cooling system in the affected facility malfunctioned, and the temperature inside the building began to rise. As the servers detected the rising temperature, their built-in thermal protection mechanisms activated. Some servers throttled their processor speed to reduce heat generation. Others shut down entirely to protect their components from permanent damage. In a well-designed system, the workloads on those servers would have been automatically migrated to other servers in other availability zones, and the customer impact would have been minimal. The control plane should have detected the failing servers, declared them unhealthy, and restarted their workloads elsewhere. But in this case, the scale of the cooling failure exceeded what the automated recovery systems were designed to handle. The thermal event affected a large portion of the data center simultaneously, and the automated failover processes were overwhelmed by the sheer volume of workloads that needed to be relocated at the same time. The control plane tried to restart thousands of virtual machines on the remaining healthy servers, but those servers were already running their own workloads. The sudden addition of thousands more workloads overwhelmed the remaining capacity. Some of the destination servers became overloaded and themselves started experiencing problems. The automated system, trying to fix the problem, was making it worse by creating additional demand on infrastructure that was already under stress. The result was an outage that lasted several hours and affected customers running workloads in that region. The failure started as a physical problem, a cooling malfunction, but the impact was amplified by the very automation that was supposed to contain it. The automated systems that elegantly handle the failure of one or two servers could not handle the simultaneous failure of a large fraction of the data center's capacity. This is a tension that runs through all of cloud infrastructure. The more you automate the response to failure, the better the system handles routine, small-scale failures. A single server going down is handled instantly and invisibly. But the same automation can struggle with large, unusual failures that exceed its design parameters. The automation was designed for the common case, and the common case is the loss of a few servers, not the loss of an entire building's worth of computing capacity. This phenomenon, where the response to a failure makes the failure worse, appears under several names in the distributed systems literature. One is the thundering herd, where a service fails and then recovers, and all the clients that were waiting for it rush back simultaneously, creating a spike of demand that can overwhelm the service all over again. Another is a cascading overload, where a load balancer detects that one server is unhealthy and redirects its traffic to the remaining servers, which now receive more traffic than they were designed for. And if they cannot absorb the additional load, they fail too, and the load is redistributed again to an even smaller set of survivors. The defenses against these patterns include exponential backoff, where a client that receives an error waits for a random, increasing amount of time before retrying, spreading the retry traffic over time instead of concentrating it in a single spike. They include admission control, where a service sets a maximum number of concurrent requests it will accept and rejects additional requests beyond that limit, preserving its ability to serve the requests it has already accepted. They include priority-based load shedding, where a service under stress deliberately drops low-priority requests to preserve capacity for high-priority ones. And they include careful capacity planning, maintaining enough reserve capacity that the loss of a significant fraction of the infrastructure can be absorbed without overloading the remainder. But each of these defenses involves trade-offs. Exponential backoff slows down recovery. Admission control means some legitimate requests are rejected. Load shedding means some users get errors. Reserve capacity means paying for servers that sit idle most of the time, waiting for a failure that may not happen for months. Every defense has a cost, and the engineering challenge is finding the configuration that provides adequate protection at an acceptable cost. Let's now turn to the human side of cloud failures, because the technology does not operate in isolation. It is designed, built, configured, deployed, and maintained by people, and human decisions are woven into every aspect of how the systems behave. The Uptime Institute, an organization that tracks data center reliability, publishes annual reports on the causes of outages. Their research consistently shows that human error is the single largest category of causes for significant data center outages, not hardware failure, not software bugs, not natural disasters. Human error, misconfigured settings, commands entered incorrectly, maintenance procedures performed out of sequence, failures in communication between teams during a complex operation, assumptions about system state that turned out to be wrong. The Facebook outage we discussed was triggered by a human-initiated command that contained an error. The AWS outage was triggered by an automated system, but that automated system was designed, configured, and maintained by human engineers who had to make decisions about its behavior, its thresholds, and its scaling parameters. The Azure cooling failure was a physical malfunction, but the automated recovery systems that could not handle the scale of the failure were designed by human engineers who had to make assumptions about how large a failure the system would need to handle. This is not a criticism of the people involved. The systems they build and operate are among the most complex engineering projects in human history. The decisions they face about configuration parameters, automation boundaries, scaling thresholds, and failure handling strategies involve trade-offs that are genuinely difficult and often impossible to evaluate fully until a real failure reveals the consequences. These engineers are exceptionally capable, and they learn from every outage. Each major incident produces a detailed post-mortem analysis, a thorough root cause investigation, and a set of corrective actions designed to prevent the same failure from happening again. The post-mortem reports that the major cloud providers publish after significant outages are some of the most valuable documents in the field of distributed systems engineering, because they describe in detail what went wrong, why the defenses did not catch it, and what changes were made to prevent a recurrence. But the corrective actions from one failure cannot protect against the next novel failure. They protect against a repeat of the specific failure that just occurred. The next outage will be caused by a different combination of factors, a different chain of events, a different set of conditions that nobody anticipated. The nature of complex systems is that they produce a practically infinite variety of failure modes, and the engineering effort is a continuous race against that variety. There is a concept in the study of complex system safety, developed by researchers including James Reason and Richard Cook, that helps explain why this is so. James Reason described a model he called the Swiss cheese model of system failure. Imagine multiple slices of Swiss cheese stacked together, where each slice represents a layer of defense against failure. One slice might be the automated monitoring system, another might be the peer review process for configuration changes, another might be the redundant power supply, another might be the capacity planning that ensures reserve resources are available. Each slice has holes in it, gaps or weaknesses in the defense. Maybe the monitoring system has a blind spot for a particular type of failure. Maybe the peer review process misses a subtle error in a complex configuration change. Maybe the backup power takes a few seconds longer to activate than expected. Most of the time, the holes in one slice are covered by solid cheese in the next slice. A failure passes through one layer of defense but is caught by the next. The monitoring might miss the failure, but the redundant system absorbs it anyway. The configuration error might not be caught by peer review, but the automated validation catches it before deployment. But occasionally, all the holes line up. A failure passes through every layer of defense, all the way through the stack, without being caught by any of them, and emerges on the other side as a visible outage. The specific combination of holes that aligned is unique. It has never occurred before and will probably never occur in exactly the same way again. But a different combination of holes will align next time, because the cheese is always full of holes, and the system is always being changed in ways that create new holes while closing old ones. Richard Cook, a physician and researcher who studied safety in healthcare and later applied his work to software systems, formulated what he called the law of stretched systems. The law states that every system operates at a level of capacity that is pushed toward the boundary of its limits. As a system is made more reliable, the demands placed on it increase to match. When engineers fix a failure mode and increase the system's capacity or resilience, the additional capacity is filled with new workloads. The system is always operating near the edge of what it can handle, because the edge is where the most value is extracted. This does not mean that the engineers are reckless or that the operators are negligent. It means that the economic and operational pressures on the system naturally push it toward full utilization. A data center with 50% of its servers sitting idle is wasting money. A network with 90% of its bandwidth unused is over-provisioned. The natural economic pressure is to fill the capacity, to use the resources, to extract value from the investment. And as the system fills toward its capacity, the margins that absorb failures become thinner. The consequence of the law of stretched systems is that large-scale failures, when they do occur, tend to be severe. The system does not have large reserves of unused capacity waiting to absorb a major failure. It is operating efficiently, which means it is operating near the point where the loss of a significant component can overwhelm the ability of the remaining components to absorb the load. Let's talk about another dimension of cloud failure that is less dramatic but in some ways more insidious than the spectacular multi-hour outage that makes the news. This is the quiet, partial degradation that affects individual users or individual applications without ever rising to the level of a declared incident. A cloud service might experience elevated latency, responding to requests not in milliseconds but in seconds because of congestion on a network link or high utilization on a shared storage system. A user might experience this as a web page that loads slowly or an app that feels sluggish, and they might attribute it to their own internet connection rather than to a problem in the cloud infrastructure. An individual virtual machine might suffer poor performance because it is sharing a physical server with another customer's workload that is consuming more than its expected share of resources. This is sometimes called the noisy neighbor problem. Your virtual machine has been allocated a certain amount of processor time, memory, and network bandwidth, but the physical resources are shared, and if another virtual machine on the same server is running an unexpectedly intensive workload, the competition for shared resources like memory bandwidth, cache space, and network capacity can degrade your performance even if you are technically receiving your allocated share. A DNS resolution might fail for a subset of users in a specific geographic area because of a misconfigured routing rule at one of the provider's points of presence. An API might return errors intermittently because of a race condition in the software that manifests only under specific timing conditions that occur rarely, but not never. These partial failures are harder to detect, harder to diagnose, and harder to fix than complete outages. A service that is completely down produces clear, unmistakable error messages and immediately triggers alarms. A service that is degraded for 2% of users can persist for hours or days before the pattern becomes visible in the monitoring data. The affected users may not report the problem because they assume it is on their end, or because the problem is intermittent and difficult to reproduce. The cloud providers operate extensive monitoring systems that collect thousands of metrics from every component in their infrastructure every second: CPU utilization, memory usage, disk latency, network throughput, error rates, queue depths, response times. Automated alerting systems compare these metrics against expected baselines and flag anomalies. But the sheer volume of data creates its own challenges. An infrastructure with hundreds of thousands of servers generates millions of data points per minute, and distinguishing a genuine problem from normal statistical variation in that enormous stream of data is a significant technical challenge. Machine learning is increasingly used to help with this detection, training models on historical data to recognize patterns that precede failures and to distinguish between harmless fluctuations and signals of genuine problems. But machine learning models produce false positives, flagging anomalies that turn out to be nothing, and each false positive contributes to alert fatigue, a condition where engineers begin to pay less attention to alerts because most of them are noise, and the models can miss novel failure modes that do not resemble anything in their training data, because a failure that has never happened before produces a pattern that the model was never trained to recognize. The balance between monitoring sensitivity and alert fatigue is one of the persistent operational challenges of running large-scale infrastructure. Too little monitoring means real problems go undetected until users complain. Too much monitoring means the operations team is drowning in alerts, most of them false, and the important signal is lost in the noise. Let's now talk about something that many people think about when they consider the cloud, even if they do not articulate it precisely, and that is the question of where, physically, their data is located and why it matters. When you store data in the cloud, it is in a specific physical location. The provider knows which data center, which rack, and which storage device holds your data, or more precisely, which devices hold the fragments of your data if it has been erasure-coded across multiple devices. But you, the customer, typically do not know these details, and in many cases, you are not told. You choose a region when you configure your cloud resources. and the provider handles the placement within that region, according to its own optimization algorithms. The physical location matters for several reasons. The first is latency. Data that is stored in a data center in Northern Virginia reaches a user in New York faster than it reaches a user in Sydney, Australia. The speed of light in a fiber-optic cable is roughly 200,000 kilometers per second, about 2/3 the speed of light in a vacuum, because the light is traveling through glass rather than empty space. A round trip from New York to Northern Virginia and back, about 700 kilometers of fiber, takes roughly 3.5 milliseconds just for the light to make the journey, plus processing time at each end. A round trip from New York to Sydney, roughly 32,000 kilometers of fiber for the full round trip, takes about 160 milliseconds just for the light. That difference is perceptible. A web page that loads in 50 milliseconds feels instant. The same page loading in 300 milliseconds feels noticeably sluggish, and the user can feel the delay even if they cannot articulate what is causing it. Content delivery networks, commonly called CDNs, address the latency problem by caching copies of frequently accessed content at locations around the world, close to the users who request it. When a user in Sydney requests a web page that is served from a data center in Virginia, the CDN may already have a copy of that page cached at a location in Australia, and it delivers the cached copy directly without fetching it from Virginia. The first user who requests the content after the cache expires still experiences the full cross-Pacific latency, but subsequent users in the same area get the faster, locally cached response. CDNs operate hundreds or thousands of edge locations worldwide, typically situated in internet exchange points and co-location facilities in major cities. The large cloud providers operate their own CDN services, and independent CDN companies like Cloudflare and Akamai operate extensive global networks of their own. Together, these CDN networks form a layer of infrastructure that sits between the origin data centers and the end users, absorbing traffic spikes, reducing latency, and protecting the origin servers from the full force of user demand. The second reason physical location matters is legal jurisdiction. Data stored on a physical server in a physical building is subject to the laws of the country where that building is located. A database stored in a data center in Frankfurt, Germany, is subject to the European Union's General Data Protection Regulation. A database stored in a data center in Virginia is subject to United States law, including laws that may allow government agencies to compel the provider to disclose the data under certain circumstances. A company operating in Europe that stores its European customers' personal data in a US data center may find itself caught between two incompatible sets of legal requirements. This has driven the cloud providers to expand their geographic footprint, offering regions in an increasing number of countries so that customers can choose to keep their data within a specific legal jurisdiction. It has also driven the development of data residency controls, features within the cloud platforms that allow customers to specify where their data may be stored and to prevent the platform from moving it outside the permitted regions. These controls are becoming increasingly important as more countries adopt data protection regulations that require personal data to remain within their borders or within defined trade blocs. These jurisdictional questions have become one of the most active areas of policy debate in technology governance. The European Union, Brazil, India, China, Russia, and many other nations have enacted or are developing data localization requirements that restrict where personal data can be stored and processed. For the cloud providers, compliance with these requirements means building and operating data center capacity in an ever-growing number of countries, each with its own regulatory framework, its own infrastructure challenges, and its own operational costs. The geographic expansion of the cloud is driven not only by demand for low-latency access, but by the legal requirements of national sovereignty over data. The third reason location matters is physical risk. A data center in the Gulf Coast of the United States is exposed to hurricane risk. A data center in Japan is exposed to earthquake and tsunami risk. A data center in a river floodplain is exposed to flooding. The cloud providers consider these risks when selecting locations for new data centers, and they design the facilities to withstand the local hazards. Earthquake-prone regions get seismic bracing and base isolation. Hurricane-prone regions get hardened structures and elevated equipment. But no design can eliminate all physical risk, and the history of data center incidents includes events triggered by natural disasters that exceeded the design parameters. Let's take another pause and think about the scale of what we have walked through tonight. There are entire cities' worth of electrical power flowing continuously into these windowless buildings. There are cables lying on the ocean floor, stretching between continents, carrying pulses of light that represent the data of billions of people. There are millions of servers running billions of virtual machines and containers. There are layers upon layers of software managing, monitoring, orchestrating, replicating, routing, and recovering, making thousands of decisions per second without any human involvement. And every time you open an app on your phone, send a message, check your email, or watch a video, you are reaching into this infrastructure, touching these systems, relying on this machinery to be working. Your request travels from your device through your local network, across the internet backbone, into a data center, through layers of switches and load balancers and firewalls, to a virtual machine or container running on a server, in a rack in a row, in a building that you will never see. And the response comes back the same way, in a fraction of a second, and the whole thing feels like nothing happened at all. The fact that it works as well as it does, that billions of people use it every day with barely a thought, is a genuine engineering achievement. The people who design, build, and operate this infrastructure have created something that is, by any reasonable measure, one of the most complex systems human beings have ever built. It is more complex than the electrical grid. It is more geographically distributed than the telephone network. And it is more dynamic than either of them, changing its configuration millions of times per day as workloads scale, traffic shifts, and new services are deployed. But the same complexity that makes it capable also means that its failure modes are complex. The cloud does not fail the way a simple machine fails. A light switch either works or it does not. A data center either has power or it does not. But the cloud is not a single machine or a single data center. It is millions of machines, connected by a network, managed by layers of software, configured by human decisions accumulated over years. And it fails in subtle, cascading, system-level ways, where the original cause and the visible symptom may be separated by many layers of abstraction and many kilometers of fiber. And that brings us to what is perhaps the most important lesson that emerges from studying how the cloud works and how it fails, which is that redundancy has limits. We talked about how data is erasure-coded across availability zones. We talked about how applications can be deployed across multiple regions. We talked about redundant power feeds, battery backups, diesel generators, redundant network paths, and multiple submarine cables. All of these are forms of redundancy, and they all work. They work extremely well, the vast majority of the time. But redundancy protects against independent failures. Its core assumption is that the failure of one component does not cause the failure of its backup. One availability zone fails, and the others keep running, because they are physically and logically separate. One power feed fails, and the other keeps running, because it comes from a separate source. One submarine cable is cut, and the traffic shifts to the others, because they follow different paths across the ocean floor. The failures that defeat redundancy are the ones that violate this assumption of independence. These are called correlated failures, and they are the most dangerous class of failure in any redundant system. A software update that contains a bug might be deployed to servers in all three availability zones at the same time, because the deployment system is designed to push updates quickly for consistency. All three zones experience the bug simultaneously, and the redundancy across zones provides no protection because the cause of the failure is present in all of them. A misconfigured network policy might propagate to all routers in a region within seconds, because the configuration management system is designed to ensure consistency across the fleet. When the configuration is wrong, the consistency guarantee means it is wrong everywhere at once. A shared dependency, a single authentication service, a single DNS resolver, a single internal network might be used by services running in all availability zones. When that shared dependency fails, all zones are affected, even though they are physically independent, because the logical dependency crosses the physical boundary. The Facebook outage is a perfect example of a correlated failure. The BGP withdrawal affected all of Facebook's data centers simultaneously because the configuration change propagated across the entire backbone. The physical infrastructure was spread across multiple locations with independent power and cooling, but the routing configuration was shared, and when it failed, the geographic distribution provided no benefit. The cloud providers work to reduce correlated failures. They deploy software updates in a staged rollout, one zone at a time, waiting for each zone to run the new version for a period without problems before proceeding to the next. They isolate shared dependencies per zone where possible, running independent instances of critical services in each zone. They design configuration management systems with guardrails, automated checks that validate a configuration change against a set of rules before allowing it to propagate to the full fleet. They test for correlated failures by simulating the loss of multiple components simultaneously, not just the loss of one. These protections add complexity, and complexity creates its own failure modes. A staged rollout is safer but slower, and it means that different zones are running different versions of the software during the rollout period, which can create compatibility issues. An isolated dependency requires 3 times the infrastructure and 3 times the operational effort. Guardrails can malfunction, either failing to block a bad change or blocking a good change that is urgently needed. Each protection creates new surface area for new types of failure. There is no configuration of the system that eliminates all risk. Every design involves a trade-off between reliability, cost, speed of deployment, operational simplicity, and the ability to respond to rapidly evolving requirements. The cloud providers navigate these trade-offs continuously, guided by years of operational experience and the accumulated lessons of past failures, and they navigate them well. The cloud is remarkably reliable for what it is, a system of extraordinary complexity running at planetary scale. But perfect reliability is not achievable. It is not a practical limitation that could be overcome with more engineering or more money. It is a fundamental property of complex systems. A system with enough components, enough interactions, and enough continuous change will always produce emergent failure modes that were not anticipated by its designers. This is not a flaw in the engineering. It is a property of the domain. What the engineers can do, and what they do with impressive skill, is manage the probability and the impact of failures. A well-designed cloud service might achieve 99.99% availability over a year, which means less than about 53 minutes of total downtime. Some critical services achieve 99.999%, which is about 5 minutes per year. These are impressive figures, achieved through the layered defenses we have discussed, the redundant hardware, the automated monitoring, the chaos testing, the incident response procedures, the post-mortem learning. But the downtime is not distributed evenly. It does not arrive in neat 5-minute segments spread evenly across the year. It tends to arrive in concentrated bursts, a single outage lasting hours, surrounded by months of perfect operation. For the users affected by that single outage, the annual availability statistic is an abstraction that does not match their experience. The honest picture of the cloud is this: it is extraordinarily reliable, far more reliable than the infrastructure most companies could build and operate on their own. It handles routine hardware failures invisibly and automatically, thousands of times per day. It survives single points of failure, single zone failures, and many kinds of multi-component failures through its layered defenses, but it is not infallible. It fails, and when it fails at scale, the effects are widespread and the recovery takes time. The failures are rare, But they are not zero, and they will never be zero, because the systems are complex, the demands are always growing, and the physics of hardware, the logic of software, and the imperfections of human decision-making all impose limits that no amount of engineering can fully overcome. There is another piece of the cloud's infrastructure that is so fundamental, so deeply embedded in how everything works, that most people never think about it at all. That piece is the domain name system, commonly called DNS, and it is worth understanding because it is one of the most common single points of failure in the entire internet, cloud or otherwise. When you type a web address into your browser, the browser does not know how to reach that address directly. Web addresses are names, human-readable labels like a company's website or a service's endpoint. But the internet routes traffic using numerical addresses, sequences of numbers that identify specific machines on specific networks. Before your browser can connect to a web server, it needs to translate the human-readable name into the numerical address. That translation is performed by DNS. The DNS system is a distributed database spread across thousands of servers worldwide. When your browser needs to look up a name, it sends a query to a DNS resolver, typically operated by your internet service provider or by a public DNS service. The resolver checks its cache to see if it already knows the answer from a recent query. If not, it contacts a series of authoritative DNS servers, starting from the root of the hierarchy and working down through the domain structure, until it finds the server that holds the definitive answer for the name you are looking up. The answer is returned to your browser, cached for future queries, and the connection proceeds. This process happens billions of times per day across the internet, and it usually completes in a few milliseconds. But when DNS fails, the effects are immediate and sweeping. If the DNS system cannot translate names to addresses, no browser can find any server, no app can reach any service, and the internet, from the user's perspective, simply stops working. The servers are still running, the data is still there, the network links are still carrying traffic, but nobody can find anything, because the naming system that tells everyone where everything is has gone silent. DNS outages have caused some of the most widespread internet disruptions in history. In October of 2016, a distributed denial-of-service attack against a DNS provider called Dyn knocked out access to dozens of major websites and services across the eastern United States and parts of Europe. Twitter, Reddit, Netflix, Spotify, GitHub, and many others became unreachable, not because their servers were down, but because the DNS infrastructure that translated their names into addresses was overwhelmed by the attack traffic and could not respond to legitimate queries. The cloud providers operate their own DNS services, both for their internal infrastructure and as managed services for their customers. Amazon's Route 53, Google's Cloud DNS, and Azure's DNS service each handle enormous volumes of queries and are designed with the same layered redundancy we have discussed for other infrastructure components. But DNS remains a critical dependency that sits at the very base of the stack, and its failure affects everything above it. Let's also look at how the cloud handles one of the most challenging problems in all of computing, which is keeping data consistent across multiple copies in multiple locations. We talked about how storage services replicate your data across availability zones for durability, but many applications do not just store static files. They use databases, systems that manage structured, constantly changing data with complex relationships between records. A banking application needs to track account balances that change with every transaction. An e-commerce platform needs to manage inventory counts that change with every purchase. A social media platform needs to track the relationships between billions of users and the content they create, share, and interact with. When a database runs on a single server, consistency is straightforward. Every read sees the most recent write because there is only one copy of the data. But a single server database is a single point of failure. If that server goes down, the database is unavailable. So databases in the cloud are typically replicated across multiple servers, often in different availability zones. to provide both durability and availability. The challenge is that replicating data across multiple servers introduces a fundamental tension. When a user writes new data, that write must be propagated to all the replicas. Until all replicas have received the update, different replicas hold different versions of the data, and a user reading from one replica might see stale information that does not reflect the most recent write. This tension was formalized in a theoretical result known as the CAP theorem, published by the computer scientist Eric Brewer in 2000. The theorem states that a distributed data system can provide at most 2 of 3 properties simultaneously. Consistency, meaning every read returns the most recent write. Availability, meaning every request receives a response. And partition tolerance, meaning the system continues to operate even when the network between nodes is disrupted. In practice, network partitions do happen, especially in systems spread across data centers that may be miles or hundreds of miles apart. So the real choice is between consistency and availability during a partition. A system that chooses consistency will refuse to serve reads or writes during a partition, rather than risk returning stale data. A system that chooses availability will continue to serve requests during a partition, but some of those responses may be stale or inconsistent. Different cloud database services make different choices along this spectrum, depending on the use case they are designed for. A financial database that tracks account balances typically chooses strong consistency, because serving a stale balance could result in overdrafts or double spending. A social media feed that shows the latest posts can tolerate eventual consistency, where updates propagate to all replicas within a short window, typically milliseconds to seconds, and users might briefly see slightly stale data without any serious consequence. Google's Spanner database, which the company uses internally and offers as a cloud service, achieves something remarkable. It provides strong consistency across data centers spread around the world, using precisely synchronized atomic clocks and GPS receivers in every data center to assign globally ordered timestamps to every transaction. The clock synchronization allows the system to determine the exact order in which transactions occurred, even when those transactions happened in data centers on different continents. This is an extraordinary piece of engineering, and it demonstrates how far the industry has pushed to solve the consistency problem, but it also demonstrates the scale of investment required. Each Spanner data center contains atomic clocks that are accurate to within a few microseconds, because the correctness of the entire system depends on knowing what time it is with extraordinary precision. Most applications do not need the level of global consistency that Spanner provides. They use simpler replication strategies that are appropriate for their specific requirements. But the underlying tension between consistency, availability, and the physical reality that light takes time to travel between data centers is a constraint that applies to every distributed system, and it shapes the design of every cloud database service. Now let's talk about what happens behind the scenes when a large-scale outage occurs, from the perspective of the people who have to respond to it, because the human side of incident response is as important as the technical infrastructure, and it reveals something about how these systems are actually operated day to day. The large cloud providers maintain around-the-clock operations centers staffed by site reliability engineers, often called SREs. The site reliability engineering discipline was formalized at Google in the early 2000s by an engineer named Ben Traynor-Sloss, and it has since been adopted across the industry. The central idea of site reliability engineering is to apply the principles and practices of software engineering to operations problems. Instead of manually configuring and maintaining systems, SREs write software that automates the operations work. Instead of responding to every alert by hand, they build automated remediation that handles common failure modes without human intervention. And instead of measuring success by uptime alone, they use error budgets, an allowed amount of unreliability that balances the need for stability against the need for rapid feature development. The error budget concept is worth pausing on because it reflects a sophisticated understanding of how to manage complex systems. A service with a target availability of 99.99% has an error budget of roughly 52 minutes per year. As long as the actual downtime stays within that budget, the service is meeting its reliability target. If the service is well within its error budget, the development team has room to deploy changes aggressively because they can afford some failures. If the service has already consumed most of its error budget, the team slows down deployments and focuses on stability. The error budget creates a quantitative framework for making trade-offs between reliability and velocity that would otherwise be subjective and contentious. When a large outage occurs, the operations center initiates an incident response process that follows a structured protocol. An incident commander is designated, and their job is to coordinate the response, not to diagnose the problem personally, but to ensure that the right people are working on the right aspects of the problem, that communication is flowing to the affected customers, and that decisions are made in a coordinated way rather than by individuals working at cross purposes. The diagnostic work during an incident is often extraordinarily challenging. The engineers are dealing with a system that is partially functioning and partially broken, and the symptoms they can observe may be far removed from the underlying cause. A customer sees that their web application is returning errors. The application team sees that the database is not responding. The database team sees that the network latency to the storage system has increased dramatically. The networking team sees that traffic is being rerouted through an unexpected path. The infrastructure team discovers that a fiber link has been taken offline for maintenance that was not communicated to the networking team. Each team sees a different symptom, and the root cause is buried several layers below the most visible effects. The post-mortem process that follows a major incident is one of the most valuable practices in the industry. A well-run post-mortem is blameless, meaning it focuses on understanding the systemic factors that allowed the failure to occur, rather than identifying individuals to blame. The reasoning behind blameless post-mortems is pragmatic, not sentimental. If engineers fear blame, they will hide information about near misses and contributing factors, and the organization will lose the opportunity to learn from the incident. A blameless culture encourages full disclosure, which produces better post-mortem analysis, which leads to more effective corrective actions. The post-mortem document typically covers the timeline of events, the root cause analysis, the contributing factors, the impact assessment, and the corrective actions. The corrective actions are the most important part because they represent the concrete changes that will prevent the same failure from recurring. They might include adding a new monitoring check, modifying an automated system's behavior, changing a deployment procedure, adding a validation step to the configuration management process, or increasing the capacity reserve in a particular component. These post-mortem documents, when published externally, are among the most educational resources available for understanding how large-scale distributed systems fail and recover. Amazon, Google, Microsoft, and many other companies publish detailed accounts of their major incidents, and the accumulated body of these reports forms a kind of case law for distributed systems reliability, a growing record of failure patterns, contributing factors, and effective remedies. The people who do this work, the site reliability engineers and the infrastructure engineers and the operations teams, work in a domain where perfection is impossible and the consequences of failure are immediate and visible. They build systems that handle routine failures invisibly. They respond to extraordinary failures with structured discipline, and they learn from every incident to make the systems more resilient for the next time. It is quiet, demanding, often unglamorous work, and most of the world has no idea it is happening. Let's touch on one more dimension of the cloud that shapes its physical reality, and that is the economic structure that determines where data centers are built and how they are operated. Building a large data center costs hundreds of millions of dollars. The land, the construction, the electrical infrastructure, the cooling systems, the networking equipment, the servers, and the security systems add up to an investment that only the largest companies in the world can make at scale. And the operating costs are continuous. Electricity, which is the largest ongoing expense, runs into millions of dollars per month for a single large facility. Maintenance, staffing, equipment replacement, and network connectivity add more. The economics drive the geography. Data centers cluster in locations that offer cheap electricity, favorable tax policies, reliable power grids, access to fiber networks, and proximity to population centers. Northern Virginia became the largest data center market in the world, partly because of its proximity to Washington and the density of government and corporate customers in the region.